This lecture is an introduction to formal logic. An important starting point is sets. So you want to think about how to define sets. You could list all the members of a set. That is to say, for example, S equals, and I just say this set which I'm defining contains 1, 2, 3, and let's say 5. The problem doesn't work for infinite sets, and not fun for large sets. Now, a common alternative: describe the set precisely. One example of this, let's give an example. This would be to say the set of all even natural numbers. Okay? Written in sort of the standard notation, this would be the set of n in, say, n, such that n is divisible by 2. And there's other ways to define this divisibility, but it's not important right now. This is formal enough. Problem: what if I can't commonly or exactly characterize this set? Now, what if I was not, I didn't have the language to exactly give a characterization where anything which satisfies my characterization is what I want in the set, and anything which does not is not present in the set, or anything I do not want in the set does not satisfy the characterization. Now, what if I don't know exactly what is in the set, but I know, or what characterizes the set, but I know how to obtain the elements of the set via a specific process. Okay? Now, this is sounding kind of vague, I'm sure, to you, but this is going to make some sense. Now, inductive, and this is the way of defining sets which we are going to focus on. This is inductive definition of sets. And maybe I'll make this a bigger title. Here are the components. Universe, core, and operations. Now, what is the universe? The universe is a large ambient space from which I know my elements come from. Now, this is not the exact set I want, but I know my set will exist somewhere in this space. Example, let's just say the set of all people Okay, and let me bold this example. The set of all people. Okay, now the core, let me see basically what can I just define to be in the set. This is going to be axiomatic elements of my set. So in this example, let's just continue the same example. Uh, let's just say you in the same set of people. So in terms of people, we'll say you. Now, operations. Operations on elements of my set, which my set is closed under. Now, in the same example, this will be parent or child. So, basically, what this example is illustrating is using inductive definitions, I can generate someone's family tree, you could say, without exactly characterizing it. Because if I were to say characterize all members of your family tree, you might have a hard time doing this. But if I were to say that I'm in my family tree, and now anyone that I can get to using the parent function or the child function, and there's some problems with this definition in that parent, if it's a uniquely defined function, then how does this work with multiple parents? But if you ignore that problem for now, anyone who I can get to from me who is a member of the set of all people who can be reached as a parent or as a child from me is part of the set. That's the idea. Now, result, uh, set of all relatives. Okay, so we're going to say universe equals U, core equals C, operations equals O. And now define I of U, C, and O as the set of elements starting in C this is actually an easier way. Let's say start with C. In a sense, we'll say S0 implies or is equal to C. S1 equals C unioned with all possible applications of O to members of S0. Now, and maybe this is more accurate to say result of all possible applications of O to members of S0. And you can sort of continue this process to say Sn equals Sn minus 1 union result of all possible applications of O to members of S n minus 1. So it's like you can keep sort of building this incrementally. Now, this is sort of an intuitive way to understand how you construct elements. So, if I were to say core equals all equals 0, and operations equals S, like some function called S, you can imagine. So what I mean by this is that I start with an element, so it's like X, which maps to S of X. And S of X is just going to be formal, like it's just the symbol S of X. And this is the operation. You can imagine the set will be the set 0, S of X, S of X, and dot dot dot, and you can sort of say this is like a construction of the natural numbers, if you're familiar with that. Now, formal definition of I U C O. This will be the minimal subset of U containing, I don't know, I have this in the math, containing C, which is closed under the operations in O. Okay? And hopefully this makes sense. Now, you may sort of argue, like, how do you know that this such a minimal, sort of unique minimal exists? And here's what you can justify. Let's just say exercise. Suppose S and T are subsets of U containing C, which is closed under the operations in O. Then S intersect T. This also has the same property, which means there is a unique minimal. Let's say theorem. For all U and C, subset of U, and every O over U, let's say, just for clarity, there exists